Hello, everybody. Welcome to the G2M Research webinar on computational storage and EDSFF for flash devices. This is sponsored by NGD Systems, Supermicro, and Lenovo. Let's give everybody a minute or two to log in, and then I'll go ahead and start with the agenda. All right, let's go through the agenda and the panelists. So I'm Mike Human. I'm the Managing Director of G2M Research. You can see our website there. Feel free to go there if you want to see more recordings of webinars like this and other ones we've done. They're all there. Joining us today as sponsors are Scott Shadley, Vice President of Marketing at NGD Systems. Also we have with us Jonathan Hinkle, who's a Principal Research in Systems Architecture at Lenovo, and Mike Scriber, who's Product Director at Supermicro. Thanks everybody for joining us on this. So from a schedule standpoint, we'll spend the first 8 or 9 minutes kind of going through a few slides I have on the NVMe SSD market, talking a little bit about ground rules, then we'll go into Scott's presentation, followed by Mike's, and then Jonathan's, and in between each of those, we have some audience survey questions. These will be polls you get to take online interactively. After that, we'll do about 8 to 10 minutes of Q&A and wrap it up. We should be done around 10 o'clock. Or around 11 o'clock, I'm sorry, these are off by an hour, around 11 o'clock Pacific time. Couple housekeeping things. If you have questions, please use the Q&A window in Zoom to type them in. That way everybody can see them, and we'll save all the questions to the end. And we will also be recording this session, and we'll also make the slides available. That will typically happen 1 to 2 days after the recording is, or after the webinar is completed. And we'll send a note to everybody that registered saying, here's where you can get the recording, and here's where you can get the slides. So with that, let me jump into my part real quick here, and we can get started. So kind of starting out, one of the first questions I want to kind of hit is, what is a flash SSD? So a real simple view, and this is not meant to be a rhetorical question either, is that it's a bunch of NAND chips just stuck on a board with some sort of controller on there. You can have some amount of RAM, some have more, some have less, and that can impact performance. Some have management capabilities built into the controller, some don't. So that's kind of the classical way of looking at what an SSD is. And there's a lot of different form factors, everything from 2.5-inch drives to PCI Express add-in cards to M.2 drive, and some new form factors that we'll talk about in a little while. Flash is one of those sort of things, if you thought about it 7 or 8 years ago, you would have said, I don't see how this is going to really change IT. I think those of us who lived in the disk days and are looking at things today would say it's had a massive impact on IT. If you think about it 10 years ago, prior to Flash really becoming in the mainstream, storage systems, both local storage and network storage in the form of centralized arrays, was always a long pole in IT performance, right? If you think about, enterprise storage arrays 10 years ago, the big EMC boxes and things like that, they always had tons of RAM. They had the fastest disk drives you could get, and and they would oftentimes short stroke them, which means they're only using a piece of it, of the disk drive, so they could improve performance. These things were $1 million boxes, I mean, literally. And even with that, we were talking about latencies that were in the millisecond range. That was good. Flash has really changed that. Now we talk about latencies in the microsecond range. I mean, we're even if it's network, we're near local performance. And and if you look at NVMe Express or NVMe Express, it will even reduce that further. So given all that now today, we're really in a situation where the network and the PCI Express bus are the long pole from the performance standpoint. In fact, I saw a study recently that said in a lot of data centers, they figure they're using as much energy to move data as they are to actually do computation on the data. That's certainly a change from where we're at 10 or even 20 years ago. So with all that, it sounds like enterprise SSDs are kind of like the panacea for but we still do have some challenges with them, and some of our panelists will talk to those as we kind of go through this today. So, if you look at capacity, it continues to increase, and it's increasing at a rate that's even faster than Moore's law. It's still exponential. But the form factors we're using are legacy form factors. If you think about PCI Express cards, obviously, This is a form factor that's designed for I/O cards. You know, you look at like Fusion I/O is one of the first people to use it for a flash card. They can hold a lot of flash. That's the good thing, but the negative is you can't hot swap them. They eat up I/O slots, and we'll have some of our other panelists talk about that more. M.2 is kind of the other end of the spectrum. These are small cards, you know, maybe a quarter size of a credit card or even less. Very low cost, but also fairly low capacity. You know, 2 to 4 terabytes is pretty big for an M.2. Another problem with them is they're not hot swappable. You can't take one out. They are in the server. And if you look at U.2, right, which is the disk drive format, the 2.5-inch disk drive format, it's not optimized for flash chip layout or airflow. So you really have some issues trying to max out the capacity of those. With all that said, if you look at kind of shipments in NVMe flash, U.2 is a clear winner. There are 3.7 million units shipped in 2017. That's about 4x growth over 2016. As of our last report, the last G2M research report, there are 29 different models of U.2 drives, and we'll be coming out with another report in December, so we'll update those numbers. And they're coming from every major storage vendor that's out there. M.2 is also showing good growth. It grew about 50%, up to about nearly 2 million units last year. 25 models there, mostly from some of the leading storage vendors, Samsung obviously being one, Intel being another. There's a variety of people making these. PCI Express add-in card SSDs are roughly flat. They shipped about 250,000 units in 2017. That's actually, and there's less models than there were in 2016. So that one is slowly but surely going away. So last slide of mine before we jump off to our panelists. So what does the future hold for enterprise SSDs? There's a new form factor that's come out. It's called EDSFF, and I'm sure some of our panelists will talk in detail about that. It's tailored for flash media density and layout from a geometric standpoint, better airflow, much higher densities. It can be hot swappable or is hot swappable depending on which of the form factors used, and there are multiple sizes. This is called the EDSFF long, which is what we're showing here. There's a short version, and there's also a version that looks like an M.2 drive. It's a little wider, so you can fit more flash on it. So those are all coming along, and those are starting to see this year. We started to see actual systems and devices in the EDSFF form factor. One other thing that we're seeing is companies are also adding new capabilities to SSDs. I know at least one of our guests is going to talk about computational storage and adding that to SSDs. There's also companies that added network and flash interfaces to SSDs. In addition to things like increased redundancy and error correction, you know, if you look at the SSD market, it's really become more than just adding more capacity and more performance. It's what else can we put in this to kind of help offload compute and networking and improve the overall situation for the data center. So with that, I'm going to jump to Scott. Scott, I'm going to pass you control here and go for it.
Sounds good. So again, welcome to everybody who joined us. So we put this together looking at things, kind of trying to take a look at what's coming in the 2019 and kind of beyond. We're all presenting different material sets around different ways that we're all implementing NVMe storage solutions. And as you heard from Mike, historically, flash storage has just been exactly that, just storage. We've been working on some new stuff, and we've got some opportunity to talk to some future directions of storage capabilities. So this particular set of slides, I kept it much more educational, just to try to illustrate what's going on. Certainly you can follow up with me or ask questions, or just go to our website and see some more nitty-gritty details. So what basically we're talking about is, as storage is growing, we're all creating more and more data. So you're going to hear from Mike and Jonathan about ways you can hold your storage, but the storage footprint itself is just becoming more complex and too difficult to manage. So historically, we pull all our data out of the drive, stick it into host memory, and let the compute do its thing, flush it out and redo it. But as we continue to proliferate from cloud into fog, into edge, and all these wonderful new ways of doing things, and the amount of storage each of these are holding, it's becoming almost impossible to transfer the data fast enough. So it becomes not a data size problem or even a data footprint problem. It becomes a data transfer or data movement problem. And so that's where the concept of compute to data, computational storage comes into play, and the kind of the direction of what NGD Systems is focused on. We're adding that compute capability into the flash storage device itself. And so I have a fun way to talk about this. Hopefully it'll make sense to a few people in the room, but if you think about a standard SSD, we've got really, really fast storage, but there's a bottleneck. And we open that bottleneck from SAS and SATA with NVMe, but it's still a skinny pipe. You add more lanes, you're just clogging those lanes with the amount of data you have. So by taking a standard SSD and putting some processor offload into the drive, it now becomes an intelligent SSD, and you have the ability to provide users more flexibility in design and a scalable solution that every drive you add to a system, you have to put storage in your box anyway, so why not make your storage do something more for you? And some of the key focuses we talk about from our perspective is we follow the KISS principle. Keep it simple, stupid. So don't make any massive changes to the host platform. Use standardized footprints like Linux and the APIs and SDKs and even Docker for virtualization. Don't play around with trying to replace the CPU, but optimize the footprint and facilitate the most efficient TCO you can possibly get out of the platform. And that's really what the focus of what we were doing is I need to make a power efficient, large capacity, smart or intelligent SSD, hence bringing intelligence to storage. And one way to look at that is if you think about today in all these wonderful things that we call data lakes, in today's data centers, as you can see, I have a data center lake here. Somewhere in the midst of that little poor fisherman, which is you, me, and every other user on the planet, is looking for the orange fish. And if you look close, there's an orange fish buried in there. I put them in there on purpose. And historically, the only way that we can search that data lake or any of that data in that massive data set is to bit by bit pull the entire data set into memory, execute the application, flush that data back into the lake, and then look for the fish again, and it becomes very inefficient. Really, you can drain the lake, but then you have the complications of everything around that if you were to do it as a one-stop shop. So what we talk about from an NGD perspective is why not have that orange fish just jump right in the boat or jump right out of the water. That's what computational storage does, is it executes the search for that missing fish inside the lake itself and has the lake present the fish for you. And when we talk about it from a premise of computational storage, orange fish, you can think Nemo and trying to find Nemo. It's great looking for Nemo, but remember, there's a lot of Dories out there who don't remember where the data is in the first place. So having something where the capabilities of the storage architecture allows the data to present the solution and not simply a bunch of data is where computational storage comes in from a higher order perspective of what can be done. Now, as we think about this and we hear this term, computational storage as a technology has been around from our perspective for 5 years. We've got some friends in the marketplace that have been doing it for 4 years, some less than that. But not every one of us is doing it the same way, which is a challenge, but is also an opportunity. So what I wanted to do next was talk about the different paths that exist today. So this is looking at all of the market for computational storage solutions, and several of us that are here that are actually presenting this are at the Supercompute show where these are all on display. So you can see that the original version was to take an FPGA, put it behind a bridge and stick a whole bunch of drives behind it. Then our friends at Samsung came out with the Smart SSD, which put an FPGA in front of an SSD all on one board. There's others that have just an FPGA solution that manages a certain amount of flash, but also has iterations related to host managed FTL, which goes all the way back to the concepts of the problems, if you will, that existed with Fusion IO. And then from our perspective, we've decided to make it the most ease of use and highest density and lowest cost solution you can get. So we actually built an ASIC-based version of this platform. So you can see the number one difference between all of these is there's only one computational storage ASIC, which is also the NVMe controller. And it is a single point solution, which gives you the footprint to be able to deal with what the next two speakers are going to talk to, which is these unique new form factors and petabyte scale architectures while still offering the capability to have compute. So these are all viable ways to get to this marketplace. They all do different things in different ways, and they all solve problems for our customers and for us as users around managing data. And it's from that perspective that we looked at it and said, we're going to try to find the most generic yet friendly way to implement a computational storage solution. And that's what NGD's products look like. So what does that mean for you as a user? We do have a proprietary NVMe controller, and one of the big things that came out of that so far today at the event, especially when it comes to talking to any three-letter acronyms or anybody in the U.S. government, it's a U.S. fabbed ASIC, so it's the only NVMe SSD controller built in the U.S., and it happens to have computational capabilities installed in it. We do offer the AIC card, which Mike mentioned, and the reason we still have that is the capacity. You can see that we can make a 64 terabyte drive, and there are people buying those today. That U.2, that slightly less friendly but very familiar form factor, we can do 16 and even 32 terabytes with some of the new NAND announcements that have come out. And of course, M.2 and EDSFF form factors, as those are where some of these data center and petabyte scale architectures are going to be talked about from Jonathan and Mike. So from an NGD perspective, we built a ground up NVMe SSD. And if you want to buy a very high capacity or very low power, cost effective SSD, I can sell that to you as an NVMe SSD. If you want compute capability where you have the ability to have hardware acceleration, built-in ARM processors, or even a full-fledged OS on the drive, that is where the secret sauce of the NGD platform comes into play. And we're currently sitting on just over 22 patents for this architecture and these technologies, anywhere from the silicon itself all the way up through and including the in-situ processing. Now, I've talked about why we need it. I've talked about the various different ways to implement it and the fact that several are done in very different ways. And then I've shown you my particular product solution. The key now is as we move forward, there was an announcement yesterday where SNIA, the standards body, which will be talked about later related to the form factors, has decided that this market is real and needs help to make sure that you guys, all of the consumers of this product technology, are capable of implementing it in an easy and simple way. And as part of that effort, being one of the founding members of it, we were voted in as the co-chair, as you have to have two chairs for all SNIA twigs. My friend Tom Friend is also the other co-chair. We'll be driving these activities to make this even more capable of falling into that keep it simple, stupid principle, making everyone on the line be able to implement a computational storage solution in a much more efficient way. So all kinds of goodness, new SSD controllers, high density capabilities, compute inside the drive, and now standardization of that footprint. Everything's lining up to make a very solid platform moving forward. So that kind of wraps up the section I have. I look forward to following up with some of you in the Q&A and as far as that part of it goes. And now what we want to do is give it a chance for our friend Mike at Supermicro to talk about how they're implementing it today and see what they have to offer for us from that perspective.
Well, before that, thank you, Scott. And before that, we have one poll question, so let's go ahead and get that done first, and then we'll go into Mike. And by the way, thank you, Scott, for not making me have to do the Finding Dory thing on you there. So Finding Nemo, whichever it was. So I'm going to launch the first poll question. Yeah, there you go. So I'm launching the first poll question. You should see it pop up on your Zoom window. If you don't, just go up and pull down the polls menu. You should be able to see it. The question is, does standardizing computational storage via SNIA make you more likely to adopt it within the next 12 to 24 months? And just choose one of these. We'll give you a minute to fill it out, and then we'll jump into Mike Schreiber's presentation.
No, I don't get to vote.
No, panelists don't get to vote.
I was going to try to help you out, Scott.
That's all good. I appreciate it.
Listen, yeah? No, I'm kidding.
We're having some fun with that one.
Exactly. All right, give it another 10 seconds, and we'll wrap it up. And the results of these polls will be in the slide set when we put it out, too. All right, I'll just share the results here real quick so you can see them. And with that, let me go ahead and flip to the next slide and pass control over to Mike at Supermicro. Mike, all yours.
Awesome. Well, thank you very much. My name is Mike Scriber. I'm a Senior Product Director at Supermicro. Supermicro has been really stepped out very, very early in NVMe, and we now have over 150 systems that use NVMe. So kind of an early adopter of the whole NVMe thing. So what I want to start with is a lot of what we've kind of already talked about. And that is, what are the form factors? This just kind of shows some of the Intel form factors, focusing on that. M.2, U.2, the add-in card, and then what Intel came out with most recently is the ruler. And that doesn't go into EDSFF. There's actually a difference between ruler and EDSFF. I'm going to talk a little bit about that. We're also going to talk a little bit about what Samsung is doing. But I want to take it from the perspective of these are way cool devices. Love the computational aspects of it too. That's way cool. How can we make a system out of these devices, and what can we do with that? And so that's where I may have control, but it doesn't want to work. There we go. So we kind of came up with some requirements. We said, if I was going to make a system, what would I want to do? Well, one of the things we'd really like to do is, wouldn't it be great to be able to put a petabyte of flash into a 1U? Can that really be done? And with these new devices, it's pretty easy. But even with old devices, maybe we can still fit a petabyte in a 1U. And you would do that, of course, if you had 32 hot swap drives and 32 terabytes in each drive. That would give you a petabyte. Of course, we also want to make sure that we have all the enterprise features: hot plug fans, hot plug power supplies, toolless kind of drive carriers, and then all of the accessibility type of things, meaning I've got remote access to power on and off the system, to power on and off each individual drive, to do all of those kind of things that I would do from a management perspective. And then I want to have great performance. If I'm going to make this box, one of the things is I want to put as many lanes possible. That was a great showing how many lanes and how you're still kind of packed in there. So what if I had 64 gigabytes per second of data transfer rate? That would help to alleviate all of that clogging that's going on. So that was another thing we wanted, and obviously a very scalable design. And then what a lot of people have seen is one processor or even a dual processor system really can't do all of the computation if you're going to have a petabyte. So maybe we need to connect in more, like maybe up to eight host servers to connect into this device to really utilize all of the power that you've got, all of the bandwidth, all the capability you've got in these drives. So this is what we designed first. We said, all right, given that idea, let's start with U.2. U.2 has been around for a long, long time. How could we do this with U.2? So how we did that is we made this is a JBOF, the JBOF version of it, where we've got 64 lanes of PCIe going out the back, 8 hot swap fans, we've got redundant power supplies, but the most important thing is out the front, we've got this sled that you can pull out and access the drives on the sides. And you're like, well, how does that really work? And don't I have to power the system down to do that? Well, you really don't. We've designed it such that with this umbilical cable in the back here, you can slide the entire tray out while it's still running. And we've got 32 lanes of PCIe just across that cable, which is kind of amazing. That was one of the big challenges, is how do you make an umbilical cable that'll work the way it does? And I won't go into all the details because we don't have that much time. But we also put this really great toolless drive carrier in here so you can easily access the drives, push the button, it locks in, push the button again, and it pulls out. And I can have 8 drives on this one side, 8 drives on the other side, and then 2 trays, which gives me 32 drives. One of the keys, you're like, how can you possibly cool that? I mean, it's hard enough to cool 32 drives in a 2U. How are you cooling, 24 drives in the 2U is pretty common. How do you do that? And the real key here, you probably can't see my cursor, unfortunately, but that back plane has been rotated by 90 degrees. So normally the back plane blocks all that airflow. By rotating it by 90 degrees, we allow all of the air to flow right across those drives and not be blocked by the back plane. So that was one of the key things of the design. So where would you use such a thing? Well, anything where you need a lot of high throughput ingest. If you have a burst buffer, for example, now that I'm at SE18 right now, I'm hearing a lot about burst buffers, right? How do we just dump a whole bunch of data really, really fast. Well, that's high throughput ingest. Or high density hot storage. You just need a lot of hot storage, but you don't want to take up an enormous amount of space. HPC data analytics is an obvious thing. My favorite on the video streaming is I wish Netflix would buy one of these, because then I wouldn't ever have to wait for another movie again. It would be great. Content delivery network is another application, or just putting at the top of rack storage, just an enormous amount of storage that everybody can use. And this kind of shows that on the right-hand side, different ways that you can connect a 2-node, a 4-node, or 8 nodes to connect into this system and get an enormous amount of bandwidth. We have a 4-node, what we call a big twin. It's in 2U space, 4-node. We connected that up, didn't tune it, didn't do anything, and got 52 gigabytes per second of bandwidth out of the box and 13 million IOPS. So an enormous amount of performance. So then we had some people say, well, that's great, but I don't want 2 servers. I just want 1 server accessing that, especially for like a software-defined storage application where I really just need those processors to run my software-defined storage software and access all of those drives. Wouldn't that be great? So we designed this system that has 2 Skylake processors. Obviously, we'll be going to the next generation processor that Intel's talked about, the Cascade Lake. And we were managed to fit in 24 DIMMs. So you can get 24 DIMMs of memory and 2 PCIe slots. And those are by 16. Each one is on a separate processor. So it's a very symmetric design. Each processor can access all 32 drives. And you've got by 16, so you can get 100 gig on each processor, or 200 gigabit out the back. So that's what we're doing with the server version of U.2. But then we're like, well, with this modular design, couldn't I slide that tray out and replace it with a tray using a different form factor? And that's where we started going into the Intel Ruler. The Intel Ruler has some really cool advantages to it. And I say cool, meaning thermally cool. It's also pretty cool looking too. But the real advantage of going with the Ruler design is this ability to not have that blocking airflow with the backplane. You'll notice here in the upper right-hand corner, the backplane, instead of being vertical and blocking the airflow, it lies down flat and has a vertical connector that allows the air to flow right through it. And each one of these orthogonal connectors is a by 4. So you get by 4 PCIe going off to each one of the drives. It allows for all of the air to flow in there and not be blocked. And that's one of the key things. And these connectors are designed to not only handle PCIe Gen 3, but also be prepared for Gen 4 and Gen 5. So it really is kind of future-proofed for that plan. So this is how we were able to then take it, replace those sleds, those drive sleds, with Ruler drive sleds. And so you can see on the far left-hand side, this is our JBOF version, where instead of U.2 drives, you end up with the Ruler drives. And then we also have, of course, the server version, because it was just as easy to do that. Replace that sled, shorten the umbilical cable, and have the ability to have this in a Ruler form factor. So why rulers? Really, it has everything to do with the ability of the Ruler to fit in a 1U, to give an enormous amount of capacity in that 1U, and to drop your total cost of ownership, because the minute you improve those thermals, what that means is your fans now can run at a lot slower, and you can really have much greater thermal efficiency. One of the things about the Intel drive that I really like is they put thermal grease on every component inside that drive, connecting it to the outside case. So this aluminum case becomes one big heat spreader. So thermally, it's a great solution. So we talked a lot about Intel, and Intel's going to be very happy that I did that. But Samsung also has their own solution. So with Samsung came out with what they originally called the M.3, and this, guess for some reason they couldn't call it an M.3. I guess that name was used by someone else. So they called it the next generation EDSFF, and that was really hard to say. So I'm really glad they changed it to NF1. That's a whole lot easier. So the NF1 drive, as you can kind of see there, is much smaller. It's more in the size of an M.2 at 110 millimeters. So with this NF1, you can make a much shorter chassis, and you think, well, how are you going to get the capacity? Well, actually, the NF1, they've already announced that they're going to fit 16 terabytes on that small little drive. And then you say, well, why? How is an NF1 different than M.2? Well, one of the big differences is instead of lying flat on a board like an M.2 connector, you prop it up vertically, and it's hot pluggable. So M.2 is not unpluggable, and that's one of the struggles that we've had with using M.2 is people want to be able to hot plug a drive. Well, with the NF1, you have the ability to hot plug the drive, and this system, once again, it's a 2-socket server, 24 drives. Once again, very much a symmetrical design so that you've got half the drives on one processor along with a by 16 slot, the other half on another processor with another by 16 slot, so you get 200 gigabit Ethernet out the back, or InfiniBand, or whatever it is you want to plug into those by 16s. So some real benefit with the NF1 system. And so this kind of summarizes that. You can see what one of those drives looks like down at the bottom, and it shows that it's 30.5 millimeters high, and then that same 110 millimeters that's used for the M.2. And if you look at that connector really close, it looks just like an M.2 connector. And that's where Intel and Samsung kind of parted ways. Samsung was very much saying, we need to have backwards compatibility to M.2. Intel said, no, that's not really important to us. We want to focus on a different form factor. So both of these, when we're talking about Intel Ruler, some people also call it Gen 1 for Intel, and then the NF1 are proprietary designs. You can only buy them. Intel has their Ruler, Samsung has their NF1. So that's where in the future, what we really needed is we needed to have some sort of combined spec that was more public and open that we could then use for a standard form factor that other people could build, and we could have multiple vendors on. And that's what we're leading into in the next conversation that Jonathan's going to do, because what we've done is, you've heard of EDSFF in the presentation. We have a system. I'm going to back up just a hair. We have an EDSFF system that fits perfectly into this Ruler chassis. We had to obviously change the connector, so the connector is a little bit different. It uses the Gen Z connector. But we only had to modify one board to use that connector, slight changes to the latching on the chassis, and we have the exact same JBOF and server type of products, but now with EDSFF, now that we have a standard that we can use. And I'll let Jonathan talk to that, because he was the godfather of EDSFF.
Excellent. Thanks much, guys. Let me do the next poll here. We'll go to that quickly. All right, we're going to launch the second poll. So the poll question is, how much total capacity do you require for each all-flash system that you deploy? Choose one answer, and after that, I will give it about a minute, and then we'll move on to Jonathan Hinkle, the godfather of EDSFF. Jonathan, we expect you to star in at least one movie and one sequel. Godfather 3 is kind of forgettable, so but watch for at least Godfather 1 and 2.
This is where he'll get mad at me later.
Later?
Oh, never mind. Yeah.
All right, well, you're 20 seconds.
Yeah, and I have seen there are a few questions, as Mike mentioned. We'll hit those at the end, and if they're not already answered by then, we'll certainly get to them as we get towards the end of it. So thanks again for continuing to put in the questions. We'll get around to those as soon as we get towards the end of the presentation.
All right, we'll give it another 10 seconds, and we'll go ahead and share the polling with everybody.
Pointed out that I shouldn't have said gigabytes. That should be terabytes, right? Not gigabytes. So a typo on this page.
Terabytes are better. Definitely.
Yes, 64 terabytes to 128 terabytes. All of that should be terabytes up to a petabyte.
So turn the G's to T's and you're good.
Yep, exactly. So I was at supercompute yesterday talking about megabytes of data, and the guy's looking at me going, really? And I'm like, oh no, I mean gigabytes per second. So I'm like, oh geez.
Well, I'll date myself. The first laptop I got was in 1985. It had 10 megabyte hard drive and a 3.5-inch floppy, and that was like the coolest thing on the planet. So
yeah, I still have
obviously
my
that wouldn't do much today, would it?
No, nothing.
All right, and with that, let's go ahead and Jonathan, I'm going to give you control, and we can go ahead and launch it off. Go for it.
Okay. Hi, this is Jonathan Hinkle. I'm a Lenovo senior researcher. Basically, I'll try to live up to my newfound reputation or role as a godfather. But I'm going to talk about EDSFF. And really, you see in the title here, mainstream NVMe for the masses, so the data center masses especially. Here, in case you haven't gotten the decoder ring, EDSFF stands for Enterprise and Data Center SSD Form Factor Working Group. All right, let's see if I can click the slide. Almost, there we go. All right, so data center servers. We have a lot of different types of systems. Obviously, hopefully a lot of people are familiar. The rack, the 19-inch rack especially, but rack servers in general are the predominant types of servers in the data center you'll find today. And in that rack, there's a lot of different form factors, but they're pretty much all that fit that paradigm of 19-inch. You have 1U, 2U, 4U. You have half rack, you have 7U. So there's lots of different types of systems, but most of the servers today are this rack mount. And it's interesting because we have this 1U unit. Most of them actually still follow this 1U unit. There's a lot of reasons for that, including just the height of a DIMM or how much you can cool in a certain processor power. But in general, 1U is that common building block. So you'll find 2U systems, 4U systems, but it's all multiples of that 1U. So 1U is really that common parameter, mechanical parameter across servers as far as that height. As far as across SSDs for the data center, we've had just a certain number of options. We've had adapter cards, we have consumer SSDs, we have HDD form factors. Really, first SSDs, you had compact flash cards that we plug into an IDE bus. Later, we got to something that we could actually plug into the SATA or at the time SCSI, or you could do ATA kind of HDD form factor. And so that was perfect for first adoption. SSD could just be plugged in and adopted very easily, where you have a hard disk drive slot, and it gave you that speed up. But obviously, it didn't give you just the full capabilities of flash. It was really just still in that interface to the HDD. Then, of course, we went to adapter cards with PCIe interface, which is another existing slot in servers, because you now get the PCIe interface for lower latency, which is a lot better fit for flash. And Fusion IO led the way, and now NVMe obviously is really leading the charge there. And then the consumer SSDs, we had SATA. We've had SATA, which is a great first SSD. The M.2 was designed. First, it was MSATA. There was a bunch of different SSD form factors, which were perfect and designed for a laptop. And M.2 is still sort of that reigning king for laptops. And now we have NVMe drives as well for consumer SSDs. Unfortunately, none of these are optimized for the data center and for flash. So if you look at an adapter card, you get this really high performance caching, and that's what it was designed for, I/O acceleration. But you're stealing PCIe slots. So your adapter card for I/O, like Ethernet or InfiniBand, or all the different things you want to plug in that slot as a peripheral card, now you don't have that slot available because you put an SSD there. So you put storage in a place where traditionally it had not been going. Also, it's pretty big and expensive. So you have a really large chunk of capacity and performance you're trying to consume all in one card. So it's very expensive per unit. And then you can only fit a few of these in a system. So it's very high end, good for caching, but not really a scalable storage solution. Consumer SSDs, much smaller, much more modular. Unfortunately, they were designed for laptops, so they're low capacity. They don't support hot plugs. You're supposed to be able to plug it into a laptop and screw it down so it's thin, flat. And the connector is not designed for enterprise at all. It's very unreliable for enterprise kind of needs, the 24/7 workloads. And also, once you actually adapt it to make it fit the enterprise needs, and we do use these in enterprise, then it's just a little bit more expensive, or it doesn't quite fit all the feature set that we're looking for most of the time. So it's good for boot drive sometimes in enterprise systems, but overall it's not a good fit. It's not designed for the data center. For HDD form factors, obviously has the storage feature set, hot plug, and all the other things we're looking for. Unfortunately, it's designed for rotating disks, not SSD. It blocks the airflow to the hottest components in the server. So just the good and bad and the ugly across these, none of these were a good fit for an SSD that's designed for the data center. So we needed this optimized common building block across server designs. I think you saw from Supermicro some of the things that we can do in servers now, with different types of NVMe drives. And now with the new standards we've created called EDSFF, we have a solution. So first we started with a general purpose connector that's scalable, and basically we can use this connector across all the different SSDs. So the whole point of this was to reduce this basically proliferation of different SSD types and different form factors that were none of them necessarily a good fit, and consolidate on a single industry standard solution. So with this connector, the SFF TA1002, which is now an industry standard in SNIA SFF, we've done that. And it supports lots of different orientations, widths. It can go by 4, by 8, by 16. It supports lots of different interoperable specs. So our main focus in the EDSFF group was NVMe, but it also can support other protocols like C6, which is also something that can go over PCIe. OCP MES, which is a different card in OCP that's for I/O, so that same connector can be used. Gen Z, OpenCAPI, Ethernet. This connector is very versatile, and it'll support all the speeds that we're looking for and all the feature proofing, basically our backplane designs. And then also, now we're allowed to basically break free of this HDD form factor. We can actually design systems using optimized SSDs. We have a lot more package sites. We have better performance and better scaling. And then thermal. I think that was something that also Mike was alluding to. Basically we can get much, much better airflow because we don't have to have the same sort of brick format that the HDD, the rotating drives required. And so you see also here up on the top right, this is a right angle orthogonal EDSFF connector version. And the nice thing about this, we still have this vertical version here in the middle, but if you look at the top right here, this orthogonal one stands up straight. And so we've standardized this, so now you can actually have a horizontal backplane instead of a vertical backplane. And so with that, you don't block the airflow. So you can plug the drives right in, hot plug into this. All the EDSFF drives are all hot plug capable, and you plug it in, and then it just goes right into the backplane. So this could actually even be a single board, even without a backplane, with the same motherboard that you can plug this into. So it gives you a whole new range of things you can do, and you can see down here a lot better thermal. The top one here, there's the long version, there's a short version also, and you can see much, much better airflow in our server systems, which is critical for the drives, but it's also really critical for the rest of the components, especially the hot processors behind it. Okay, so here are the form factors. So what we did, again, we came together with seven companies, Microsoft, Lenovo, Facebook, Dell, HPE, Intel, Samsung, and we came together to form this new group called EDSFF as the promoters. And then also we have Micron and WD, Toshiba, and basically in Seagate and all the SSD suppliers, the key SSD suppliers in the industry joined this group to just get a first alignment on what do these SSDs need as a feature set. And this is finally something that we brought to SFF in SNIA, and then went through that standardization process, and now is a full industry standard. And so we have that connector that I was showing you, and then there's also 3 other types that are actually form factors for the SSDs. We have the E1.L, the E1.S, and the E3. So basically, as you were seeing, Samsung had NF1 is another thing that's not in this group, but Intel had a ruler drive, which is the long one, and that's basically reflected very similarly in the E1.L after we negotiated all these different form factors and the connector and everything that's in these. For the E1.S, I started a research project back in 2015 to start this as a form factor, something that's a little bit more similar to a DIMM size. So it's taking up that full space of the 1U. And that's really what's reflected here is the E1.S. And then the E3 is a larger form factor that sort of can be a replacement for 2.5 inch once that starts running out of steam. The beautiful thing here is these all use the same protocol. They're NVMe, they all have PCIe interface, they use the same connector, they have the same pinout and functionality, the way that you use them. But they have very different usage cases within the systems, but you have the same expectation and know how to use them, know how to design for them. So the one that I'm most familiar with is the E1.S, the EDSFF 1U short. Again, it's the SFFTA 1006 industry standard. The vision there was originally create this new standard that's optimized for the data center and really designed to be able to scale SSD content in the data center. So it's mainstream NVMe drive. It's compact and modular in the form factor. It fits vertically in the 1U, and it fits in the depth of a 2.5-inch drive, which is really important to allow for systems to even be retrofitted if you would like with this. It's very high capacity and performance. It's actually larger than an M.2 significantly to give you more placements of flash, at least 4 to 8 more placements, depending on what your M.2 design is. And then it supports hot plug and the enterprise feature set. So this connector is robust. It's going to run up to, I think, 112 gigabits per second is how fast you can run this EDSFF connector. Has been tested. It's already been run. So we have a lot of future proofing here. If you want to run, for example, 25 gig with C6, or if you want 32 gig with PCI Gen 5, this will run those different faster speeds and seamlessly keep scaling. We can leverage our investment in our system. So this is going to be a longevity play, something that we can use over time. Also, 12 volts is the main power that we've used to the drive that allows us to scale the power and not have to worry about VLRs and voltage regulators like if it's 3.3 with the M.2, that'd be a big problem for us. Also, LEDs are integrated, so we don't have to have light pipes. So we've reduced cost overall and made something that's really optimized around the actual system design as well as for the SSD. So this is something that allows us to move past sort of the caching, tiering kind of approach and go more to main storage and sort of. Let's see. So I think the next slide here will show a little bit more of the key system benefits. This can go obviously in any of those different servers. They're all based on that 1U, so now you can put it everywhere. So it's a common building block that can go everywhere. It's much smaller, enabling that high density storage. You can fit at least 6 to 8 drives where you can fit 2.5-inch drives, so 3 to 4 times the number of drives. Still, you got that better airflow. Also, you can get much better scaling, so you can have smaller units and a higher volume number of units that give you more performance there, but you don't have to pay for a high-end SSD. You can scale it and get some volume on it. Also, the lower base infrastructure and drive costs. So there's a lot of key elements of this where we can just leverage this one drive across all our portfolio of systems, and we don't have to keep going back to different types of drives like you've been seeing as basically a lot of dispersion in the past in the industry. Okay, so basically EDSFF is this new form factor for SSDs. It's higher power, higher bandwidth. The EDSFF connector supports well over 40 watts. I think it's maybe 70 plus. So higher power E1.S, E1.L, they all support higher power. It's really just a question of thermal, but you get better thermals with this connector and this form factor. And then the key point here is also, it's not even just SSD, it's even past that. It's actually something that can grow, because it's a PCIe interface to this connector and to this backplane that we can plug in the front. You can make SSDs with it. Certainly, that's the first application, the NVMe drive. But you can also make NICs. You can put FPGA accelerators, persistent memory, other different types of accelerator. There's a lot of different applications where we see this growing and allowing for a lot of flexibility. This common connector and a set of form factors that allows for these different use cases. So here's the standards. They're all in SFF under SNIA. They're accessible. They're publicly accessible. Feel free to go and download those specs today. I think that's it. Thank you, everybody.
Thanks, Jonathan. We have one more poll question to do, and then we'll go into the QA. So let me launch this next poll question here. And that question is, what are the biggest challenges today in designing data center systems for NVMe flash storage that you see in your organization? And you can choose as many of these responses as you want. We'll give you a minute or so to go ahead and fill out, and then we'll go into the Q&A. And we'll jump right into the Q&A. So the first question from Andrew Boggs, and we'll just go around the panel and let you guys answer it. We'll probably start this one with Jonathan, though, the godfather of EDSFF. Seems fitting. So the question is, do you think the EDSFF specs will eliminate the U.2 and M.2 form factors, or will laptops keep them alive? Jonathan, you want to hit this one first?
Yeah, sure, absolutely. Well, and by the way, I mean, that That was actually the question for standardizing these is, it's giving you an offer. I'm going to give you an offer you can't refuse, right? So I'm trying to figure out
you could refuse trying that one, could you?
I couldn't. I was trying to figure out how I'm going to work that one in. Yeah, I mean, so I think the answer is over time, yes. So laptops today, even with U.2, that adoption is going to fall off probably. I believe M.2 will live a long, long time in laptops. It's really designed for laptops. But the EDSFF is definitely in the data center. The intent is for them to replace U.2 and M.2 long term. And then EDSFF E1.S, it could replace M.2 possibly in laptops in the long, long term. But right now, I mean, M.2 has a really good fit for laptops. So it'll probably continue it'll be a long time for that would happen.
So
Excellent.
if I could give a counter answer, because I've thought the same
Go
sort
for
of,
it.
wow, EDSFF is just going to dominate the world. The only problem I see with that is you're still going to have spinning disks. We've been trying to get rid of them forever, but they stay alive. And if you ever want to have any kind of hybrid system, it's so much easier to design a system that just supports the 2.5-inch drive form factor. And that's where I think the U.2 is going to live for a little while longer. Until we can completely get rid of the spinning rust, once the spinning rust is gone, then I think we can eliminate the U.2. But until that happens, you're still going to have the ability that U.2 gives us is SATA, SAS, and PCIe all in the same connector. Whereas EDSFF, and I think it was absolutely the right way to go, is very much focused only on PCIe for NVMe kind of drives.
Yeah, Mike.
Yeah, I'd agree with that. I think people are replacing existing disks out there too, and that's with flash drives, and obviously U.2 works well for that. So.
Yeah. I think a quick comment on that. I think you're absolutely right, and I think it's a longer term thing. I think you're absolutely right. HDD is going to live a very long time, and I didn't mean to say that. Really, the key point though is 2.5-inch HDD has stopped growing in capacity. It's a year or two ago already. So they're going end of life slowly because the capacities aren't increasing and getting cheaper for HDD. So 3.5-inch HDD is where the growth will continue, and that'll be a good complement with EDSFF as well. Yeah, I totally agree. HDD will continue to live, but
I think the hope,
capped.
The hope with QLC is that that's going to drop the price low enough that we can finally get rid of, the whole hybrid.
That's a whole nother question.
Right.
No,
what's that going to do?
To echo both of their comments to that, as well as it kind of addresses the three others that have kind of popped in. To Jonathan's point, the EDSFF for purpose-built machines for large-scale data centers and even into the tier 2, tier 3 data centers, it will absolutely take over and replace everything. To Mike's point, there are plenty of additional customers, SMB or otherwise, and just off the shelf need the flexibility. The standard server with the U.2 is going to stay as a mainstream runner. So you will see somewhat of a bifurcation of the end result, but you will see the M.2 will disappear from the data center. It'll stay in the laptop. That makes perfect sense to Jonathan's point. And then the U.2 versus EDSFF, whether they're married together in systems like that Jonathan was showcasing with some of the stuff that he's been working on, or become carte blanche one or the other, definitely going to see changes, but I don't see anything, to both people's points, eliminated completely.
All right, let's jump into the next question. And Mike, we'll give you a shot at this one, and then we'll let the other guys jump in a little bit. So we'll combine the next two questions, and that is anyone besides Intel planning on offering the ruler form factor, or will Supermicro be using this as a sole source for their design? And then there's another question, same with Samsung NF1, is it sole sourced?
Yeah, and so the actual, and this is, I'm trying to never call an EDSFF a ruler. It's hard because it looks just like an Intel ruler. So, and it looks like a ruler, and you just want to slap somebody's hand with it. And the Intel ruler, speaking of the Intel ruler as the Intel ruler, not EDSFF, that is sole sourced. It's sole sourced from Intel. Likewise, the NF1 is sole sourced from Samsung. And that's where I think Both of those designs, boy, they're going to hate me for saying it. I think both of those designs are going to go by the wayside when EDSFF finally comes out, and we start seeing products with the EDSFF short probably replacing NF1, and the EDSFF long is definitely going to replace the Intel ruler. If you talk to Intel, they kind of call their Intel ruler Gen 1 and EDSFF Gen 2. So they were very actively involved in making EDSFF, so that was part of their plan, was to do that. Fortunately for us, the transition to go from an Intel ruler to EDSFF was simple. It was one board. We redesigned the one board, changing the connector from the Intel version of the connector to the EDSFF version of the connector, and that was it. Now, unfortunately, the committee also made a tiny little change to the latch, which caused us to have to move our holes on our chassis by about 1 millimeter. So that was kind of painful. So there's a slight modification to the chassis too, but basically it wasn't very hard for us. And given all of the work we poured into the Intel ruler, it was very simple for us to switch over to EDSFF, which is why we had it displayed all the way back at Flash Memory Summit back in August. We were showing a petabyte and a 1U on the floor, and we're showing the same thing here at Supercompute.
Yeah. So I think the way that the long story short, yes, they're both unique. We do applaud, as a fellow maker of SSD technology in the space, let alone the coolness that we're adding to it. They both did something new and innovative, and I give them a credit for doing that, and the fact that they were willing to go from that new and innovative and become part of the standardization efforts. So definitely, useful products. They help drive the technology forward, and glad to see that we now come in with this standardization effort in play.
Yeah, I think that really gets to another question somebody asked, and that is Samsung's NF1 intended to be competitive with Intel's E1, and sounds like they're all working at EDSF. I think everybody started out in their own different spot, and it's all kind of converging toward EDSFF. So I think that's the answer on that one.
Yep.
Yeah, and by the way, I just one other thing to mention about that. I mean, it's not just Intel, right? And EDSFF, Micron, like actually Micron has some sample cards they've shown at FMS this year with the E1.S or the E1.L and so on. So there's actually Micron, Toshiba, Seagate, as well as Intel and Samsung who have been in the EDSFF group.
And then little guy NGD has an E1.S as well.
Yes.
Yeah,
thank you, Scott.
Yeah, there are definitely a lot of people in the EDSFF group. It is definitely an industry-wide consortium, no doubt about it. All right, last question here. This question is, what is bad and ugly about EDSFF considering the current design and future needs beyond PCIe Gen 5? So I think what the person is asking is, hey, EDSFF seems to be tied to PCI Express, and Gen 5 looks like, it's unclear where the roadmap goes after that. So, Jonathan, you want to hit that one first, and then we can go through the rest of the people?
Sure. So, I mean, I think there's always trade-offs for any type of different design. I think, compared to what we have right now, that's really why it's sort of all systems go on EDSFF. So it's really a comparison to what we have as far as the legacy versus current, future designs. PCI Gen 5, EDSFF will support, easily Gen 5, and support Gen 6 or Gen 7 probably. So again, it's like, I think Gen 5 is 32 gig likely, and so 56 gig and beyond up to 112 gig, this connector will support it, and EDSFF will support it. The use case for storage, though, I think that's a question for Flash. So for Flash, Flash may not need past Gen 5 or even really Gen 5 sometimes. So if that's the case, then that'll be just fine. We can stay wherever that makes sense for NVMe drives, wherever that sort of stalls out, if it's Gen 5 or Gen 6. But I think also what you'll see is a benefit of fewer lanes going to an SSD. So if it's a flash SSD, maybe we we'll only have to use 2 lanes instead of 4 lanes. And that would be a benefit of being able to scale without having the cabling and the interconnect cost. So that'll be an advantage. We'll see how far Flash goes on faster and faster speeds. As far as other use cases, so there's other use cases for EDSFF with the same connector. they're definitely going to go to Gen 5 and beyond, including persistent memory, for example, and other types of interfaces, different types of functionality.
So let me tackle that. Hi, Joydeep. We know each other. So let me tackle that from what's bad and ugly about it. Well, I think EDSFF is great, but if I have to be really critical of it, the criticism would be not specifically to it, but the minute you go and change a form factor, it's always challenging on the system from the standpoint of now all of a sudden I have to make it a little bit different. It doesn't fit in my chassis that I'm so used to putting U.2 drives in. I'm going to have to change things. I'm going to have to change the depth a little bit. Definitely on the long version, the long just can make the chassis enormously long. Our chassis for the EDSFF long is 36 inches long, just slightly shy of that, because we really had to struggle to keep it down to only 36 inches. It's really hard to keep a system with the long drives like that to be fairly short. The short system is nice from the standpoint of it's 110 millimeters, and you think, oh, well, great, that'll fit exactly where my 2.5 inch was. Well, not exactly, because that vertical connector, as cool as it is and as great as it does for thermals, well, it also takes up space. So it's really more in the shape of a 3.5 inch space. Well, that's still not so bad, because we've made lots of chassis with 3.5 inch drives. So it's just the change. Anytime you change, you're going to have to redo all of how you do things. And that's kind of the good, the bad, and the ugly, but that's not really a reason not to do it. You know, there's so many benefits to EDSFF. You know, it should be done, and but it's going to mean new mechanicals. I think the other thing about EDSFF short is it doesn't include the case around it. So that means for those system providers, they're going to have to figure out, how do I design a case that's going to work with this, some sort of mechanism to allow me to install it and remove it, a carrier essentially. And so it's just different, and that's all, but it's still a good idea.
Yeah.
Good deal. Hey, we have one more.
We have two, actually. One came through the chat window.
Yeah. Let's hit this other one first, though. And that question is, SNEAS has raised concerns about the NF1 connector not being electrically compatible with M.2, even though they're mechanically compatible, and that could lead to shorts on the motherboard or drives. Any thoughts? Why don't we hit this one quick, and then we can go to the next one, which I think will take a little more discussion. So, Jonathan, do you want to hit that one?
Yeah, I mean, I don't want to speak too much about it. I think I don't know what SNEA has said, but PCI SIG has sent out something recently highlighting that concern. You know, it's just I guess the current state of you know, the questions about standardization of that. So I don't have any other comment, but I think there is a comment from PCI SIG on that. So.
Yeah. And I think the nice thing is in order for NF1 to even install into a computer, you're going to need to have a carrier to make that happen. That carrier is going to prevent you from doing those kind of things. If you have the bare device, I guess you could try to cram a bare device into an old M.2 connector, and that could cause problems. I know certainly in our systems, we have carriers that'll install it, and we have little converters that'll allow you to take an M.2 and convert it such that you can plug it into the NF1 slot. So as long as you've got that converter, it's going to work just fine. And you have a system that's being shown in booth 3006. There's my little plug for SE18. Come by the booth and you can see how we have NF1 mixed with M.2 right up the front. And the way we do that is by a little converter board that makes it so that it's not an issue.
Excellent. Last question, Scott, we'll let you start this one out. It's really a two-part, and the first piece of it is, what is the difference between computational storage and traditional NVMe? The second piece is, computational storage better than traditional NVMe in terms of performance?
Yeah, so again, happy to address that one. So from a perspective of calling it a separate product, I think is a disservice to the technology. So computational storage is an advancement or an improvement upon the existing storage infrastructure that is based on NVMe. So it is an NVMe drive. It fits into the NVMe architectural system. What we're doing is simply allowing users to move compute resources that are normally done simply in the host memory and host CPU and run some of that analytics or some of those operations inside the storage devices themselves, and then they scale with those drives installed. So it's not that it's competing with or replacing traditional NVMe, it's augmenting the storage infrastructure by taking an NVMe drive and having it do something a little more than just simply store data. So from a performance perspective, if you have an entire array of 24 drives in a 2U chassis, if you're talking U.2 or 36 E1.S's, you're going to add CPU resources to that whole platform that allow you to accomplish tasks in a more efficient manner, both from a performance and power perspective, but we're not trying to replace the host system. We're trying to simply support it or augment it with this capability of computational storage.
Excellent. I think that's it for the questions. Again, thank you, everybody, for attending. As I said at the beginning, we will make the recording of this available. If you register for the webinar, you'll get a link within the next 2 days to both the recording and the slide set, so you can watch it and or download it. I'd like to thank our panelists, Jonathan Godfather Hinkle, Scott Shadley, and Mike Scriver. I had to put the Godfather first, Scott, so sorry about that.
Oh, wow.
Yeah. It's all good. He's going to come up
otherwise
with
he might,
I'm sure. So.
Yeah, otherwise you might make me an offer I can't refuse, and I don't want that. So.
As long as it stays with
And so everybody, yeah, go ahead. Sorry.
No, I was just saying it's got to stay in the family.
That's right, exactly.
Stay in the EDSFF family. That's great.
That's right.
I like that.
Oh,
I guess we should be watching out for an EDSF Part 2 and Part 3 then. Well, again, thank you everybody for attending, and we'll wrap this up. Have a great day, and we'll talk to you later. Thank you.
Thanks, everyone.
All right, thank you.
Thank you.